Hello friends, I am DSBSC, working as Assistant Professor in the Department of ECE SJBIT. In today's lecture, I will be discussing about noise. So, noise and continuous wave modulation system. In AM, that is amplitude modulation, SSB single sideband modulation, or in FM, the characteristics of the continuous wave modulation techniques we have studied already. So, this module we are going to understand the effects of noise on this modulation system. So, we are going to study about the noisy receiver model. So, for carrying out the noise related analysis, receiver model has to be used, and it is as shown in the figure. We have a message signal, noise is getting added up, not message signal, modulated signal, noise is getting added up at the receiver side. This part, it forms a receiver. So, we have a band pass filter and a demodulator. So, S of t, it is a incoming modulated signal, and the signal W of t, this denotes the front end receiver noise. So, the received signal is therefore, that is S of t, and W of t, it will be added up. The receiver has to work on this signal. So, the combined signal S of t plus W of t, now it is applied as an input for the band pass filter. So, the band pass filter has to be designed in such a way that the bandwidth of this filter, it has to be sufficient to pass the signal S of t without any distortion. So, the type of demodulator, it depends on the type of modulation we have used. Noise signal W of t, it is assumed to be an additive white Gaussian noise. So, the power spectral density of the noise, it is given by A0 by 2, where A0 is the average noise power per unit bandwidth. So, the bandwidth of this band pass filter, it is exactly equal to the transmission bandwidth of the modulated signal S of t. So, generally Fc, that is the carrier frequency, it should be very much greater than Pt. So, hence we can treat the filtered noise N of t as a narrow band noise. So, it is possible to represent the signal N of t in the canonical form. Canonical form in the sense N of t is equal to Ni of t into cos 2 pi fct minus Nq of t into sin 2 pi fct, where Ni of t, it is in phase noise component, Nq of t, it is quadrature noise component. So, this is the idealized characteristics of a band pass filtered noise. At the output of the filter, the signal present is x of t. So, which is given by x of t is equal to s of t plus n of t. So, the average power, noise power, can be obtained from this idealized characteristic. So, average noise power is equal to, what is the amplitude? N0 by 2 into 2 times of Bt. So, it is N0 into Bt. So, we need to find the signal to noise ratio at the demodulator input. So, the signal to noise ratio at the input of the demodulator can be defined as SNRI is equal to average power of signal S of t divided by average power of filtered noise N of t. SNRO, it is given by average power of demodulated message signal M of t divided by average power of noise measured at output of the demodulator. So this is a useful measure of noise performance. It is denoted as SNRO. So what are the factors affecting the signal to noise ratio at the output is the type of modulation we use at the transmitter and type of demodulation we use at the receiver. So what is SNRC? SNRC is channel signal to noise ratio and it is denoted by the symbol SNRC here. So it is defined as the ratio of the average power of the modulated signal S of t to the average power of noise in the message bandwidth W. So using these two, SNRO and SNRC, we are going to find the figure of merit. So the figure of merit, in order to compare different continuous wave modulation system, we have to normalize the receiver performance by dividing the output signal to noise ratio by the channel signal to noise ratio. So this is the figure of merit. The figure of merit should be as high as possible because higher value of figure of merit indicates that it has better noise performance of the receiver. So these are some of the important relations we are going to use. Average power of message signal is given by m square of t. Average power of k into m of t, where k is a constant, it is given by k square into p. Average power of am into cos 2 pi fmt, it is given by am square by 2. Average power of k into m of t into cos 2 pi fmt, it is given by k square p by 2. So next we will move on to find the figure of merit in DSBSC receiver. So this is a model of DSBSC receiver where we have used a coherent detection. So for achieving the coherent detection, the signal x of t has to be multiplied with the locally generated carrier cos 2 pi fct, and then this product, it has to be passed through the low pass filter. So let S of t is equal to AC into cos 2 pi fct into m of t into C. What is C? System is a system dependent scaling factor. AC cos 2 pi fct is a carrier, m of t is a signal, message signal. So the average power of DSBSC modulated signal S of t is given by C into AC into m of t by root 2 the whole square. So it will be equal to C square AC square p by 2. So the message bandwidth, it is W, and N naught is the average noise per unit bandwidth. So here AC into cos 2 pi fct, the purpose why we are using the system independent scaling factor is to ensure that the signal component S of t is measured in the same units as the additive noise component N of t. So we'll assume that m of t, it is a very sample function of a stationary process of zero mean, whose power spectral density is Sm of f, and it is limited to the maximum frequency W, where W is the message bandwidth. So the average power of the message signal, it is the total area under the curve of the power spectral density. P is equal to integral minus W2 plus W Sm of f into df. The carrier wave is statistically independent of the message signal. To emphasize this independence, the carrier should include a random phase that is uniformly distributed over 2 pi radians. In the defining equation of S of t, the random phase angle has been omitted for convenience of presentation. So we may express the average power of DSBSC modulated signal as C square AC square P divided by 2N0 into W, where C square is the constant and it is an overall this ratio, it is a dimensionless ratio. So next we wish to determine the output signal to noise ratio of the system using the narrowband representation of the filtered noise N of t. So the total signal in the coherent detection, it is expressed as x of t is equal to s of t plus n of t. So I am replacing s of t I am replacing n of t with this equation of noise. So it is C AC into cos 2 pi f C t into m of t. This is your modulated signal. N of t I am replacing it with the equation, that is Ni of t cos 2 pi f C t minus Nq of t into sin 2 pi f C t, where we know that Ni of t and Nq of t are the in phase and quadrature components of N of t, that is with respect to the carrier. So the output of the product modulator component, it is with respect to the coherent detector is V of t is equal to x of t into cos 2 pi f C t, because we have a locally generated oscillator. So substituting x of t into this equation, we will get this equation, but we know that cos square of 2 pi f C t is equal to 1 plus cos 2 theta divided by 2, and sin A cos B formula also we are very much familiar with. So substituting these formulas in V of t, we will get 1 by 2 C AC m of t plus 1 by 2 into Ni of t plus 1 by 2 into cos 4 f pi f C t into C AC m of t plus Ni of t minus 1 by 2 AC Nq of t into sin 4 pi f C t. So the low pass filter in the coherent detector, it removes the high frequency component present in V of t, which yields the receiver output. It is equal to Y of t is equal to 1 by 2 C AC m of t plus 1 by 2 into Ni of t. All the high frequency components are removed. So this equation, this one, it is indicating the following thing: the message signal m of t and the noise component Ni of t of the filtered noise N of t, it appear additively at the receiver output. That is the first point. Second point is the quadrature component Nq of t of the noise N of t, it is completely rejected by the coherent detector. So these two results are independent of the input signal to noise ratio. So thus coherent detection, it distinguishes itself from the other demodulation techniques in the very important property, that is the output message component is unmutilated and the noise component always appears additively with the message irrespective of the input signal to noise ratio. The message signal component at the receiver, it is given by C AC m of t by 2. Therefore, the average power of this component, we may say that it is equal to C square AC square P by 4, where P is the average power of the original message signal m of t, and C is, as usual, it is a system dependent scaling factor. So in case of this DSBSC modulation, the band pass filter, it has a bandwidth Bt which is equal to Bt, which is equal to 2W in order to accommodate both the upper sideband and the lower sideband of the message signal, modulated signal S of t. It therefore the average power of the filtered noise N of t, it is given by 2 times of W into N naught. So from the property of narrowband noise, we know that the average power of the in-phase noise component Ni of t, it is same as that of the filtered noise N of t. So the noise component at the receiver output is Ni of t by 2. So the average power of the noise at the receiver output, it is given by 1 by 2 into Ni of t the whole square. So it is, when we substitute this, we will get into the equation N naught W by 2. So the output signal to noise ratio for a DSBSC receiver using coherent detection, it is now given by SNRO is equal to average power of message divided by average power of noise, it is equal to C square AC square P by 4 divided by N naught W by 2. After calculations and modifications, it is equal to C square AC square P divided by 2 N naught into W. So the figure of merit, it is given by SNRO by SNRC. SNRO just now we have reduced, and SNRC it is also the same. So both numerator and denominator gets cancelled each other and it will be equal to 1. Now note that the coherent detector output in the receiver using DSBSC modulation, the translated signal sidebands sum coherently, whereas the translated noise sidebands sum incoherently. This means that the output signal to noise ratio in the receiver, it is twice the signal to noise ratio at the coherent detector input. So this is all about the DSBSC figure of merit. So suppose if the gamma factor, if it is equal to 1, it implies that SNRO is equal to SNRC. So this range of gamma is permissible. If gamma is equal to 1, means SNRO is greater than SNRC, this range is the desirable one. When gamma is less than 1, it implies SNRO is less than SNRC, so this range of gamma is not permissible. So we want the figure of merit, that is gamma, it should be greater than 1, such a way that the signal to noise ratio of the output, it is more when compared to the signal to noise ratio of the channel. So let me summarize what we have discussed in today's video. We have started with the block diagram of noisy receiver model, and we have seen figure of merit equation and the characteristics of band pass filter noise, some important relations, and then model of DSBSC receiver using coherent detection. This block diagram I have explained in detail, and then we started with the equations related to DSBSC, where you have to find two things, SNRO and SNRC, to find out the figure of merit. That is our main intention, so that you can identify that which is best. So we have the signal, modulated signal S of t, we have the noise component N of t. When those two are combined with each other, we will get X of t, and that signal will be multiplied with the local oscillator generated signal, and then the low pass filter will remove all the high frequency component. So using these analysis, we will be able to find the average power of noise and average power of the message signal. So after finding the figure of merit, we will be sure to tell which system is better. In my next video, I will be speaking about the noise in AM receiver. So here in AM receiver, we need to find again the same process. We need to find the figure of merit, that is SNRO by SNRC. So We will see that in the next class with a detailed explanation. Thank you.